Let's do something a bit different today. We're going to see how to use programming to solve a game. So this is a game called Pet Detective, which is from an app called Lumosity, which is some, I don't know, they make games that are supposed to make you smarter or something, right? They're like brain exercises. But anyway, some of them are pretty good. So this game is, you're in this car, right? And you're supposed to drive around and deliver all of the pets to their houses. So for example, you're supposed to pick up this cat and deliver it there. And you're supposed to pick up the dog and deliver it there, and the porcupine there, and this other dog here, and this turtle here, right, in this level. And you can walk, sort of along these streets. And you have a sort of time limit, right? It's 15 squares of movement in this case. Picking up and dropping off are free. And you can only hold up to 4 pets at once. So that's sort of the game, right? And you can see there are some bigger levels, right? This level is relatively straightforward. So I played some levels with this manually, and then I thought it would be a good programming exercise. So I went ahead and wrote some code that solves these puzzles. So I want to show you how that works. So I'll show you like my code solving this puzzle, and then we'll talk about the code. So I have to sort of manually input the input, which is a little annoying. So like lowercase is a pet, and then the uppercase is the corresponding house. So we'll label the pets just sort of as we go. So that teal dog is A, and that turtle is B, and then there's the cat, which will be C, and then we actually have the turtle. And then we have the edges, which is, right, these two exist, and these two don't exist, so that's why this looks like that. And then we have this dog, who we haven't seen, so we need to give him a new letter, let's say D. And then we have the house of this porcupine, which is also a new letter. And then we have the car, which we'll write by S. And then we have the cat, which we said was C. And then we have these 4 edges. And then the porcupine was E, and the yellow dog's house is D, and there's no edge there. And next we have that teal dog's house, and then we have an empty space, which we'll denote with a dot. Okay, so this is the input, right? I've just sort of transcribed this picture. That's the most annoying part of solving these. And now I can run my code, and it says it takes 15 steps, which is good, because that's exactly the time limit they give us. They give tight time limits. In this game, you have to get the correct answer. And so it gives instructions for what to do. Right, so it says go to C, and then drop it off, and then pick up B, and drop off B, and then pick up A, D, E, and then drop off D, E, A, and then you're done. And apparently that takes 15 steps. I didn't count it just now. So this is what the code does, right? You give it this sort of level in this format, and it tells you what order to pick up and drop off things. So how does that work? So it's actually just a pretty straightforward application of BFS, depth first search, right? Okay, so this is sort of reading in the input that goes on for a while. Right, we said S is for a start, lowercase is for a pet, and uppercase is for a house. So grab all the input and turn it into a 2D character array. And remember that we included the edges in that array, right? So this is really like a 4x3 grid, right? There's 4 columns and 3 rows. But actually, because it's like 7 columns, right? Because all of these edges require a column, and then all of these vertical edges require a row. So it's, it's actually like the input is 7 by 5, even though sort of the grid is only 4x3. So both the number of rows and the number of columns should be odd, right? Because you just have the edges in between each column. And then the sort of logical number of rows and logical number of columns is just like round up, right? So 7 columns translates to 4 sort of logical columns, and 5 rows translates to 3 logical rows. That's just +1 divided by 2. And now we need to sort of store a bunch of stuff for the input. So this is, does this position hold a house? does this location, right? For each location, does it hold a pet in which one? Does it have a house in which one? And also, what are the adjacencies? Like, it's storing it as a graph, right? So from a row, comma, column position to a list of positions. So we are going to sort of go through the grid and read everything in. So when we find an S, that's our start position. If we find a lowercase letter, then there's a pet at that location. If we find an uppercase letter, then there's a house at that location. We lower it here so that it matches the pet, right? So that pet's something and des something, are both like lowercase a, right? So that they line up. And then we need to check if there's edges. So for each of the 4 directions, so you're going to go in that direction, right? Let's say you're here. You can look here, 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 and here for whether or not you have an edge. So this long line of code is saying, like, is that position in bounds? And is it actually an edge? Right? So the edges are this vertical bar or this bar icon. And you can see, like, all of these squares look like that. Right. If there are edges coming out of them, they're like surrounded by these characters. So the input format is kind of nice in that sense. Okay, so check that we actually found a start position. Right, so if there is an edge, then write down that this vertex had that edge. And of course, when we're looking at the other side of the edge, we'll write down the other side of that. Okay, so that was the input reading, maybe the hardest part. And now we get to the actual algorithm. So we're going to keep track of like a parent array. So for every position, like where did you come from? Because we need to actually like read out the path at the end, right? Not just the distance, right? Because I actually want the instructions for finishing the level. I don't just want to know that it takes 15 gallons of gas. That's what they told me at the beginning. We're going to keep so the normal BFS queue, like our fun queue. So initially, we are at the start position. We've gone 0 distance. We're carrying no pets, and we finished no pets, and we have no parent, right? No one where we came from. So read off the current state. So if you're at a location with a house and you are holding that pet, then mark down that you've, put down that pet, mark down that it's done, and mark down that you're not carrying it anymore. This is like your current state, right? So we're at some position, we're carrying some set of pets, and we're done with some set of pets. And we're going to use this, well, so if we've already been to this, that state, right, this position, with this set of pets, with this set of pets already done, there's no point exploring further, like the previous time that we were there was better. So just skip this. Otherwise, mark down where we came from. This is the case where we're done, and we get to print out the path. So I'm going to skip that for now. Right? But just note, like, if we are done with as many pets as there are, then we're done. So the actual BFS part is relatively simple. So for each square that you could move to, if there is a pet there, and you're not done with it, and you are not carrying 4 things, then you are allowed to pick up this pet. So do that case, right, where you add the pet to the things that you're carrying, and now you've traveled 1 more distance, and you're at this new position, and you're carrying that new pet, and you're done with whatever you've done with before, and you came from your current state, which we labeled key. And the other thing you could do, regardless, if there is a pet there, you can actually skip picking it up. Or if there's not a pet there, or you're already full, then you can just move to the new location with whatever you were carrying before and whatever you've done with before. And this is your where you came from. It's the current state. So those are sort of the 2 types of moves you can do. Note that we handle dropping off here. And the reason is just that you always want to drop off if you can. There's no advantage to not doing that. Whereas picking up a pet, in theory, you might actually want to skip picking up a pet so that you can save space for later or something. So we need to allow you to do that. That's why we handle dropping off. So mandatorily, but picking up is a new state you can move to. Anyway, so that's actually it. And hopefully, eventually you get to a state where you are done. And then we can sort of show the path. So it took me a little bit to figure out how to show the path. You'll see that. So what do we do? We print out how long it took us. And then we're going to sort of generate our path backwards. Right, so well, we had a state that we came from. Add the current state and sort of walk back up the parent tree, right? So this is sort of the path of states that we move through to get to the end. So flip that around. That'll get us start to end instead of end to start. And then we should print out the path. So I tried, I guess, 2 versions of this. Right, the commented out thing was the first thing that I did, which was sort of printing out just the cardinal, right, like go north 1 and then east 1 and then south 1 or something. But that wasn't really as good because the controls for this are not that you like click which direction you want to go to next, is that you click a pet or a house to go to. So it's actually nicer to just show the path that way, which is what I ended up doing. So anyway, the idea is for every pair of adjacent, for every pair of adjacent states, right, you can print out what you did to get from one state to the other. So if you want to show the cardinal directions, you can say, okay, well, how did your row and column change between these 2 states? And based on how it changed, you can print out which direction you moved in. Or you can say, okay, well, did these set of things that you were carrying change between these 2 states? So if you are carrying more things than you were in the previous step, then you must have picked something up. What did you pick up? You must have picked up whatever you were carrying now. Whatever you are carrying now that you weren't carrying before. There should be one thing in that list. That's what I taken the first element. And we're saying we're picking up that thing. Otherwise, if you're done with something now that you weren't done with the previous step, you must have dropped off a pet. So figure out what you're done with that you weren't done with before. That's who you dropped off, and print out that you dropped that off. And so notice that this is not, there's actually, like the number of states in our path is 15, but the number of directions is less than 15. It's only 10, I guess, because we're not printing out things for some of the moves, right? We're only printing out when we pick up a pet or when we drop off a pet. And that's it, actually. So, like, algorithmically, this is not that complicated. It's just a BFS. Some things to notice, like designing the input format is kind of challenging. Like, I could have done whatever I want. I need something that's like easy to transcribe, right? I'm looking at a picture or like looking at the level on my phone, and I want to be able to type it in easily. So this is what I ended up with. It's kind of this visual representation. It's still kind of a pain to type these in, so I'm not sure if there's a better way or not, but I can think of one. And then also the output format, right? So it's more important to be able to type it in easily than to read it in easily, right? So there's actually a decent amount of code to like translate that into a good, stage for the computer, although it's not that bad. And the output format, it turned out to be convenient to just print out the list of instructions of what to pick up and drop off, which is not what I originally, it took me a couple of iterations to get to that, right? This is not as useful. So that was a cool thing to play around with. I guess one more thing worth remarking is like, I don't know, how fast is this, right? How big a level could it solve? So BFS is linear in the size of the graph. Every vertex has at most 4 edges coming out of it, up, left, down, and right. So the number of edges and vertices is basically the same. This is just R times C, the size of the graph. And then this stuff is expensive, right? We're keeping track of a subset of the pets that we're carrying. So every pet we could either not have picked him up yet, or currently have picked him up, in which case he's in this set, or be done with him, in which case he's in this set. So there was like a 3 to the number of pets possibilities there. So the total number of vertices in this graph is rows times columns times 3 to the number of pets, and that's the runtime that we get here. So that should be good up to, I don't know, like 15 pets or something, which is probably more than any of the levels that they're willing to give. Right? I think a computer is going to scale on this problem actually better than a human will. So it should be fine, but it's worth thinking about. Right? And this is another example of using a BFS to like store extra information. Right? In addition to where we are in the grid, we're also saying, part of the information in being at a vertex is what's happening with all the pets. Right? Are they not picked up yet? Are they picked up but not delivered yet? Or are they delivered? So we can encode that information as a crossover on the photograph. And that's what we do. So yeah, this is like a real life application of BFS, right? To actually solve this this puzzle game. So I think that's kind of neat. Right? This is not like designed to be a programming problem. It was just designed to be like a problem-solving game. But it turns out that you can use the graph techniques that we've been looking at to solve it. So I think that's neat. Hopefully you think so too. So that's it.